Hello, this video is entitled Increasing and Decreasing Functions. Alright, well, the concept of increasing and decreasing functions you've probably seen in algebra type of math courses. Now, of course, we're going to apply calculus to these ideas, but the idea of an increasing function means as you increase the value of x moving to the right along the x-axis, that means the graph y is rising, and then decreasing means y is lowering on an interval as x is increasing. So we answer these questions based on intervals of x, but it's actually determined by what y is doing, f of x. In other words, so like for this particular function, you can say that f of x, is increasing across the interval from a to b, and then we have right here, so there's a to b, then from b to c, and then from c to d would be an increasing interval. Now, some people debate on whether you should use open intervals or closed intervals. I'm not too picky about that personally. I oftentimes will use closed intervals. Now, there are some times when open intervals are mandatory. Well, first of all, if you're heading towards either infinity, you would have to use an open notation, or if it's a discontinuity. So I'm not too picky as far as you can use open notation all the time. I mean, if you wanted to, but some mathematicians might be offended if you didn't use it as a closed interval. So let's see. Now, let's see how the derivative comes into play here. Notice that I just drew a couple tangent lines as an example. I could have drawn them anywhere between A and B. But notice the slopes of those tangent lines are positive anywhere you go from A to B. Any tangent line would have a positive slope. Well, positive slope means the derivative at any value in that interval would be positive. Now you come to the middle interval, B to C. I just drew a couple of tangent lines. You see those both have negative slopes, therefore the derivative would be less than 0. And then again, you have a positive one with two positive tangent slopes greater than 0. And then notice how f prime of b and f prime of c both equal 0. You have horizontal tangent lines. So you sort of see now how the sign of the derivative on an interval being positive or negative is going to determine whether or not a function is increasing and decreasing. But we'll define that officially here in just a moment. Let's look at this next one. From A to B, the graph's clearly decreasing visually, but if you look at those tangent lines, those are negative slopes. Starting from B to C, the tangent slopes are positive in an interval that you can obviously see is increasing. Now notice this one though, f prime of b is undefined. The function's continuous. That's why it's okay to use closed brackets here if you wanted to. F prime of b is undefined. That was one of the things that I've taught in an earlier video, that if you derivatives is undefined at sharp points. So that's what's happening here. Now here's the formal test for increasing and decreasing. I don't think we're going to encounter constant too much. Constant would just be a flat line. The only way you can have a flat line, unless the entire function has a flat line, but other than that, you would have to develop as a piecewise function. You can't have a graph naturally do like something like go down, horizontal, maybe down, up again or something. It would have to be defined as a piecewise. I'm not going to mess with that. So you can't do that with just, in other words, one equation cannot generate that. So this says that if f prime of x is greater than 0 for all x in the interval a to b, so we're saying that the derivative is not defined at endpoints. Many theorems are often defined this way, like Rolle's theorem, mean value theorem, things like that. Is the function needs to be continuous in the closed interval, but differentiable in the open interval, because we're not defined at the endpoints. So you would say that f is increasing on the interval a to b. If f prime of x is less than 0 for all x in your interval a to b, it's decreasing, and then f prime of x equals 0, we have a constant. Now we're going to take functions here and we'll be able to figure this out. You wouldn't even have to graph them. You'll just be able to use derivatives and calculus and things like that, and you'll never have to even see the function if you don't want to. You can do it without it. So here's a picture I drew. Like I said, that would have needed a piecewise function to generate it. But we have increasing from a to b, constant from b to c, and then decreasing from c to d. Now these functions are stopping at endpoints, but we're mostly going to be working with infinity here. So that's going to come into play. In other words, looking at what a function is doing across an entire number line from negative infinity to positive infinity. So now, let's take a look. This is just kind of a process that I defined here to sort of do this, and of course you'll see this in action in just a moment. So, first thing you want to do is in your interval a to b, so even we assume it's for all real numbers or whatever, or if it's defined, you're looking for critical numbers and discontinuities, whether that's a hole in the graph or an asymptote, vertical asymptote. That's where changes can occur. That's how you separate your intervals into increasing and decreasing, is by finding those values. And that's how we'll break down our number line into sections, which is number 2 there. We'll separate them into different intervals. And once you have the intervals separated correctly, you don't have to test a bunch of values in each interval. All you have to do is test one value in your interval and find the sign of the derivative, and that will tell you the sign of it for the entire interval. So let's say you have an interval that goes from 1 to 4, and you pick 2 to plug into the derivative, and you know 1 to 4 is correct, and f prime of 2 happens to be positive. That means every number between 1 and 4, the derivative will be positive. So one number covers all, and that would be enough to tell you the function's increasing from 1 to 4 without ever seeing the picture. And theorem 3.5, like I said, is determine the intervals of increasing and decreasing based on whether the derivative is positive in that interval or negative. All right, now you see this is not defined on an interval, so you're assuming all the way across the number line. Identify the open intervals in which the function is increasing and or decreasing. So it's 12x minus x cubed. We take the derivative. That gives us 12 minus 3x squared. Now this won't have any discontinuity, so we're only looking for any potential critical values. So we take 12 minus 3x squared equal to 0. That gives me x squared equals 4. Very, very important here, because I often have students make this mistake on handwritten tests, is, x squared equals 4. You got to make sure you realize that's both plus and minus 2. Very important. Got to get both of them. So this is this particular textbook that I'm using it right here now is Larson. This shows how they do this. Sets it up in different these little zones here. So I just put the lines in there to separate. I wrote the intervals can be defined in either way. That's not important. So whether we have it in inequality notation right here, where it's negative infinity less than x less than negative 2, or just regular interval notation. So that's, if it's a multiple choice question, it would give you one of those two forms. So you see I have it separated at negative 2 and 2. So that gives us 3 regions we have to test for increasing and decreasing. So for the first one, I picked negative 5. Could have picked negative 3, obviously, just need something in that interval. I guess I wanted to show something just not as obvious, so I picked negative 5. Come down here, check this in the calculator. You're plugging this into the derivative, and that turns out to be negative 63. The 63 is irrelevant here. The negative is what's important. So negative means it's going to be negative for that entire interval, and negative means decreasing. So let's go to the middle interval, negative 2 to 2. I picked 1. I don't know why I did that. I normally would use 0 because that's usually an easy number to plug in. Don't know why I went with 1, but that's okay. It's certainly acceptable. Plug in 1. H prime of 1 equals 9. 0 would have been easy to plug in because you can just look at it and see that it would have been 12. But either way, 9 or 12 is positive. So positive for that interval, increasing. Next one, from 2 to infinity. Pick something larger than 2. I picked 3. I got a negative number, so that represents all tangent slopes negative. That means decreasing. So now, just for grins, I'll put the picture of the graph in there, which was not required. We essentially have, the intervals defined for the increasing, decreasing. So you see here it goes down, hits that dot, goes decreasing, hits increasing to that dot, and then decreasing again. Now you might be wondering, are these charts always going to form an alternating pattern like this? Absolutely not. So it's human nature to kind of look for any easy way to do something, which I can respect that, but no. You cannot assume if the first one's decreasing that you just start alternating them the rest of the way. That would be a bad mistake. So how about this function here? Y equals x plus 9 over x, which I'm just rewriting as 9x to the negative 1 just for derivative purposes. No point in doing a quotient rule when you can just bring it up and do a power rule. Critical numbers and discontinuities. Well, right off the bat, we got discontinuity at 0, because 0 would cause that 9 divided by 0, so that's no good. So let's take the derivative. Derivative of x is 1. The derivative of 9x to the negative 1 would be negative 9x to the negative 2. Now I'll drop it back down as a positive exponent when I set this equal to 0. It makes it easier to solve algebraically. So you can bring the 9 over x squared over. You'll get 9 over x squared equals 1. You can kind of cross multiply like this and gives you x squared equals 9. Once again, very important that we get both those plus and minus values. So it's plus and minus 3. So we have 3 separating values on our sign chart. The discontinuity of 0 and then plus and minus 3. So we must go in order for these values because we're working left to right on a number line. So I have negative 3. There's 0, and there's positive 3. So let's see. So I picked a test value of negative 4 to represent the left one. Between negative 3 and 0, I took negative 2. Between 0 and 3, I took 1. And then between 3 and infinity, I took 5. Now you might be wondering, what if it's consecutive integers, like from 1 to 2? Well, then you would have to use a decimal value. Because between 1 and 2, you'd have to use 1.5 or something like that. But that's what calculators are for. It's easy to plug in. Now I put, not showing here in a calculator, but I did label it up here for you. But this is based on me typing in this derivative function into the calculator. But to go back and graph this though, to graph the function, that's y itself. That's the original function. But we're testing these, it's hard to see that there, but sine of f prime, the sine of the derivative. So this is the derivative. So you could obviously do this yourself too. Because remember, we don't need the value, we just need plus or minus. So I put this in here, and you can see 0.4375 plus, minus, minus, plus. So it goes plus, minus, minus, plus right here, which means increasing, decreasing, decreasing, increasing. So we can take a look at the picture. So it kind of goes up right here to about right there, hits that negative 3, then down, so it's decreasing, and then coming from the other side of the 0, it's decreasing again, and then increasing from 3 forward. So there we go. All right, we got trig. Everybody's favorite. Maybe just my favorite. But I know trig's frustrating for some people, but this one you got to be careful. Good practice for, especially on that cosine squared. And using chain rule appropriately to take the derivative. So, got to be careful on the main things, the derivative, cos squared. On these problems, I don't like to, because obviously trig keeps repeating over and over and over. So we won't be using infinity on a trig problem. Strictly 0 to 2 pi. That's what I'll be using in my world. 0 to 2 pi. So we won't be doing like this. They won't go negative infinity to infinity. The first one will be 0, and the end will be 2 pi. So, kind of use chain rule. Bring the 2 down, which makes it 2 cosine to the first. So it's like taking the derivative of u squared. The derivative of u squared would be 2u times u prime, or du. So it's 2 cosine to the first, then the derivative of cosine, which will be negative sine. And then the derivative of cosine, which is negative sine, but you have a negative in front, so it makes that positive. No discontinuities in this function. I generally avoid discontinuities on trig functions. I usually just stick with sine and cosine. But if I do use something like a tangent, I would try to probably avoid the interval where there's discontinuities. But anyway, so I set this equal to 0, and you look for a factor. One thing you want to do is be careful, and same thing with regular variables. One thing you never want to do is don't ever make this mistake. Don't divide by a variable. That's a very, very bad mistake to do. And that's the same thing as with trig also. Like if you have this equation right here. I'm kind of doing this with a mouse, so it doesn't look as good as my normal writing. I'll see people take that and solve that by dividing by x. That is no good. That's no good. Because you'd get x equals 1, which is actually one of the answers, but you lose a solution. You lose the 0 solution by dividing variables. So same thing with this cosine. So you actually bring the x over, like so, and then factor out an x. So we have x, and we have x minus 1. And then you would have the two solutions, x equals 0 and x equals 1. So rule of the day, do not divide by a variable. So I factored out a sine x. In other words, I wouldn't have brought this first term over the other side and divided by sine x. That would have been wrong. So I factored out a sine x, and I designed these to where they're values off the unit circle, which I provide. So you take the sine x out, negative 2x, 2 cosine x plus 1, sine of x equals 0. Now keep in mind I'm on the open interval here from 0 to 2 pi, the open interval. Because yes, sine is 0 at both 0 and 2 pi, but leaving that interval open means I don't use 0 and 2 pi in this case. If it was a closed interval, I guess then you would, but so the only value in this open interval where it's 0 is pi, right there. Now this one, cosine of x equals 1/2, you can find it at pi over 3, and then down here at 5 pi over 3. So I have 3 values. Then once again, you see I plotted both of these equations, and then if you highlight that equal bar, that's so you see this, the bottom one's y prime. So this is the top one I would use, you don't see it here, but the top one is that I would boldface this top one if I wanted to show the graph of the original function, which I've done down here. But this is boldface to show what's going on over here. So here are my intervals. So once again, no infinity. So I'm going 0 to pi over 3, pi over 3 to pi, pi to 5 pi over 3, 5 pi over 3 to 2 pi. Now I'm using radians. You could use degree measure if you want to. That's okay. Now our answers on our intervals are going to be radians. We want radians here. But if you want to test it with degrees, but you just make sure you're in the right mode in your calculator, you can do that. Like something between 0 and pi over 3 is 60 degrees if you like to use 30 degrees. I just kind of did this in my head, which obviously you don't have to, but I picked numbers that I knew from a radian measure would be in this interval. Like for example right here, and that's actually, you don't have to get that involved. You could pick something off the unit circle. I just want to pick some easy numbers that I could just plug right into the calculator. But anyway, pi over 3, I just looked at this as saying, okay, that's a little bit over 1. Pi is a little bit over 2, a little over 3 radians. And then, so I know 2 would fit in there. So I use the same logic the rest of the way here, but you can go about it differently. You can obviously calculate those values to make sure. The last thing you want to do is pick something that's not in the interval. Well, with that being said, so you can choose these test values any way you feel comfortable. Put them all up here, and then you can see I got minus, plus, minus, plus. So this one did alternate, minus, plus, decrease, increase, decrease, increase. Oh, I was talking about the boldface equal. I didn't think I showed it, but there I am showing it right there. All right. So I'm showing the highlighting now. It's doing the top one because that's the graph. So it goes down, hits that minimum, goes up, increase, down again, decrease, up again, increase. And I'm mentioning over here that I didn't put that screen up, but I'm scaling these by pi over 3. Because if I use pi over 3, 5 pi over 3, and pi, the common denominator would be 3. So I like to scale it that way, because that way that's easier to look at on the graph if every little tick mark on the x-axis represents a unit of measure that your values are. So in other words, 1 means 1 pi over 3, 3 means 3 pi over 3, and 5 means 5 pi over 3. Relative minimum. Some books use the terminology local minimum. So either way, relative minimum or local minimum, same idea, same meaning. If C is a critical number of F, then F of C is a relative minimum of F if the graph changes from decreasing to increasing at C. Meaning that if you go down to up, you're hitting what's called a relative minimum. Unlike, the other section talks about absolute minimum. The relative minimums, I'm showing the sign chart here, anywhere it goes from negative to positive, but it's got to be at a critical number, not a discontinuity. Discontinuities cannot be local mins and maxes, so you got to be real careful with that. So if you see a changeover, but it's not it's a discontinuity, you have to ignore it. Local maximum, just the opposite. Anywhere that goes from up to down, up, down, provided not a discontinuity, up and down. Now, these arrows are not necessary. I took that same answer and just showed you down, then up, then down at these points, down, then up. Not necessary, but decrease to increase is a minimum, increase to decrease is a maximum, decrease to increase is a minimum. A lot of times on handwritten tests, I just usually have you write the answer this way. On a multiple choice test, you might have to actually get that y coordinate. I'm not sure, but it's not difficult. The main thing to remember is, so I just wrote them this form, but keep in mind f of something means your original function. Always keep in mind, even though we're using the derivative to plug your test values into, if you're trying to get a point on that graph, it always goes back to the original function. So I would have to put the values back into wherever that was, the cosine squared, cosine squared minus cosine. So for example, for pi over 3, I can kind of do this one in my head. Obviously, don't expect you to do that, but cosine of pi over 3 is 1/2. 1/2 squared is 1/4. And then cosine of pi over 3 would be 1/2. So 1/4 minus 1/2 is actually negative 1/4. So you see there's a value right there. So that y value where that red dot is negative 1/4. So the actual, this is the coordinate would be pi over 3 comma negative 1/4 on the graph. But don't only worry about that if you have to. All right, so this is what I was just saying a minute ago, but now Stewie's saying it officially. So if Stewie says it, we know it's important. Relative extrema do not occur at discontinuities. We have to watch for, all three of these. For this last one, for this trig function, they were all critical numbers, so they all had a chance. Now, not all critical numbers are going to be relative mins and maxes either. So here's one, this function f of x equals x to the 4th minus 32x plus 4. No discontinuities here, nothing to worry about. So we're trying to find the critical numbers, increasing, decreasing, and relative extrema. So all kind of coming from the same thing. In other words, once you have your increasing and decreasing chart, it doesn't take any work other than that to get the relative mins and maxes. So relative extrema is meaning plural. That means find all relative mins and maxes. So this one's not too bad. So you take the derivative as 4x cubed minus 32. And that means x cubed equals 8. So unlike x squared, you don't have a plus and minus for this. So if x squared equals 8, x equals 2. And so that's the only critical number here is 2. So there's only two intervals on your chart. So pick something less than 2, 0, something more than 2 is 4. I plugged in 0 here, and you see it's negative 30. Oh, there they are, negative 32, negative. Put in 4, turns out being a positive number in the derivative, so it's negative positive. Means we have decrease, increase. There's the graph. It goes decrease, increase. Decrease, increase means we have a relative min at 2f of 2, or if we actually needed the value, we would plug 2 right back up into here. Let's see if I can do this in my head here. 2 to the 4th is 16, minus 64 is negative 48, negative 44. Now you look at this, I'm going, that doesn't look like a negative 44 to me, but I'm guessing, especially with that fourth power, I don't have it labeled here, but I'm betting the y-axis is scaled by tens, units of 10. Just because that x to the fourth is going to make those y values get large pretty quickly. Now, f of x equals x minus 3 to the 1/3. We take the derivative of this. 1/3 x to the minus 3 to the negative 2/3. I'm just putting this 1 here to show you that I did not forget the chain rule here. I didn't forget it. Derivative of the inside is 1. So I drop the 1, leave the 3 on bottom. I drop this down. So that's basically saying 1 can't equal 0. If the numerator is always 1, you'll never get that equal to 0. So you're not going to get any critical values that way. But here's something that always befuddles many calculus students. Well, I've tried my best to really make this clear for people, but sometimes it just doesn't sink in. Technically, there are two definitions of critical numbers. The most basic one that we've already used in this section and other sections is you take the derivative of the function and set it equal to 0, which we found nothing here. But there is a second part to that definition that says if you have any values that make the derivative undefined, yet it's defined in the original function, because the one thing about critical numbers, it has to be a defined number. Critical numbers are not discontinuities. Discontinuities are important numbers, but critical means a specific definition, not critical. However, if you look at this function and you put 3 into that derivative, it'll be undefined. You go back to the original function, you put 3 in there, not undefined. It's defined. F of 3 would be 0. But what I always try to tell people, what you're watching for, now one common function is like absolute values, but I use it because they form that sharp B. But I don't usually use absolute values. I use these kind of functions. If you see a function that has a fractional exponent where the fraction is less than 1, less than 1, that's when this other case of the critical numbers is going to occur. That's when you should look for it. That's the main thing to watch for there. Now, sometimes, depending on the function, now I've done problems, and I probably did in a different section already, but where you could still get values equal to 0 and then have that same, you could have both cases applied. Sometimes I put that kind of problem on a final before, too. Well, let's say, for example, if that was x squared on the inside instead of x. Because if you took the derivative of the inside, you have a 2x, and you put a 2x out there, you set that equal to 0, you would get 0. That's a critical number. Plus the 3. You would get 0 and 3. But anyway, we have 3, so this is one of those cases. Sometimes they're sharp points, but remember the other case for derivatives not existing, yet the function still continuous, is vertical tangents. So the cases were sharp points, vertical tangents, and endpoints. That goes back into the basic definitions of the derivative and all that from the earlier chapter. So I take these functions. I pick 3 as my only value. It separates this. So less than 3, I pick 0. Greater than 3, I pick 4. I test both of them. They're both positive. There you see I have it over there. They're both positive. I have increase, increase. And you do keep these as separate intervals, though. You might think, well, increase, increase is just one big increase, but we want to keep them separate. So that vertical tangent right there, so it's like it's increasing kind of stopping for a second and then increasing some more. Relative extrema, none, because we did not change from increase to decrease or vice versa. So no extrema. All right. Find the critical numbers, increasing, decreasing, relative extrema, all that same good stuff here. We have a discontinuity at -1, automatically, divide by 0. Now we're taking the derivatives. I'm going to skip the basic, I think hopefully you can do a quotient rule by now, but just, obviously it's bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. I've heard some people tell it to me. They've learned it as if you call the top part high and the bottom part low, low d high, meaning derivative high minus high d low over low squared. So if that helps you, that's great. So I just follow the basic premise of the quotient rule. Simplify the numerator, which we do need to simplify the numerator on these because we're trying to set this equal to 0. So I simplify the numerator, combine like terms. I get x squared plus 2x minus 3 over x squared, x plus 1 squared. I set that equal to 0. And we've seen this in the quotient rule section before too, when we're finding horizontal tangent lines. Anytime that you're set, I didn't write the equal 0 step in here. Maybe I should have. If I put equal, like if that should, I'll just put it here. I won't leave this ugly thing there. But suppose that was set equal to 0. Well, anyway, anytime you're setting a fraction equal to 0, all you have to do is set the numerator equal to 0. You don't care about the bottom. In fact, another way to show it, you can cross multiply and get rid of the bottom. So the bottom's gone. So we just have x squared plus 2x minus 3. And I'm not really interested in having problems where the quadratic formula would apply, although mathematically you could. But this one factors out beautifully. So you have x plus 3, x minus 1 equals 0. So that gives you two critical numbers of -3, +1. So we have those two critical numbers combined with -1 as a discontinuity. Now, I didn't do this before. I think let me show you this little thing right here that I like to do. And this is not a mandatory part of the process mathematically, but I just do this sort of for my own benefit and hopefully the viewers' benefit too. Is I like to use a dashed line here whenever it's a discontinuity. And I just do that to give myself a mental note that, hey, that's a discontinuity. So if you change from increase to decrease, decrease to increase, it's not going to be a relative extrema. But like I said, it's not, you don't have to do that. And I'm using solid lines for the critical numbers because they have potential to be discontinuities. So that's just for my own benefit, but if that helps you, that's terrific. So I put solid lines at the critical numbers, dash line at the discontinuity. So they're the intervals, negative infinity to -3, -3 to 1, -1 to 1, 1 to infinity. So you see I did the test values all in the calculator, so I put y prime in the y1. I use -5, -2, 0, 3, and I got positive, negative, negative, positive. So it's positive, negative, negative, positive means increase, decrease, decrease, increase. Well, we had no sign change at -1 anyway, but you have an increase to decrease at -3. So it gives me a relative max of -3f of -3, and you have a decrease to increase from at 1, so it gives you 1f of 1, which of course then you could plug those x values back into the original function, not the derivative, into the original function. Because if you plug them into the derivative, you're going to get 0 every time, because that's how you got those numbers, was by setting it equal to 0. I always amuse whenever a student will come to me and go, how come when I plug these back in, I get 0 every time? It's because they're plugging them into the derivative, not the original function. I could do 1 real quick. I won't worry about -3. So 1 minus 2 plus 1. Oh, it's actually 0. Okay, so it'd be 0 over 2. So that relative min would be at the point 1, 0. Oh, and there it is right there. So it's hitting the x-axis. So let's look at the graph. We got an asymptote there at -1. It'd be nice one of these days if these calculators were programmed to show you the asymptote there. That'd be pretty slick. But increase to the dot right there, then decrease. So it's increase, decrease. On the other side of the asymptote, we're decreasing, hitting that point right there, and then increasing again. So that matches our results quite well. But like I said, notice I showed you that graph at the very end. We never had to see that graph. We didn't have to. I just like showing it to you. We had it done correctly without it. Okay. Here's another one with an asymptote. So we have a discontinuity at 0. All right, do a little quotient rule. Now I simplified this a little bit because they happen to all share a common x there, so I factor out an x. And that leaves me, once again, I just set the numerator equal to 0, and I don't care about the denominator. Negative x equals negative 8. Move the x over, that gives you negative 8. So negative 8, I just use Cn, short for critical number. So I have a discontinuity at 0 and a critical number of negative 8. So I'll put those on the chart. So there's negative 8 and 0. So my test, now once again, I did the deal just for my own benefit, maybe yours. I put the solid line to show you, and actually that's really helpful in this problem. And then I put a dash line here. And my test values, you see right here, I use negative 10, negative 2, positive 2, and I got negative, positive, negative. So I go decrease, increase, decrease. So decrease to increase at a critical number is a relative min, negative 8, f of negative 8. But here, the dashed line tells me, hey, hold on there. No matter what happens, no extrema, ignore it. Because you see it goes from increase to decrease, which could have fooled you if you thought that was a critical number. Because if it was a critical number, it would have been a max. But no, it's nothing. Ignore it. It just separates your intervals of increasing and decreasing, all it does. So here's the picture. It goes down, decrease to the dot, goes up, increase. And on the other side of the asymptote of 0, it's decreasing. So be careful with that. So maybe that dashed line does have some advantage. All right, how about a trig one here, which I believe is going to close up our video for this section. And this one doesn't have the cosine squared in it, but it's still going to be fun. I'm using the open interval 0 to 2 pi, which is common. That's pretty much what I do all the time. So this one, take the derivatives of square root of 3 sine x will be square root of 3 cos x. The derivative of cos x will be negative sine x. So square root of 3 cos x and minus sine x, you set that equal to 0, which gives me sine of x equals square root of 3 cosine of x. Now you could go to the trouble of then substituting into sine squared plus cosine squared equals 1. You could also divide by cosine and look at tangent or square root of 3. But what I'm going to do is, since sine of x is the y value in the unit circle, cosine of x is the x, I'm looking anywhere where the y value is the square root of 3 multiple of the cosine value. And that's not uncommon to find on the circle, obviously. So let me come over here. And you see where I got the check marks. Yeah, see, so if cosine is 1/2, the square root of 3 times that makes that square root of 3 over 2. So sine equals the square root of 3 times cosine. So I kind of did this without really doing the trig, working it out, so to speak. I just kind of did it by the eyeball test. And then down here you have the same thing because they're both negative. But one thing to keep in mind, suppose it would have said sine of x equals negative root 3 cosine of x. Then you would have been right here at 2 pi over 3 and then 5 pi over 3. But they're going to be the same sign because it's positive here. So either they're both positive or both negative. So with that being said, no discontinuity. So we have critical values of pi over 3 and 4 pi over 3. So I go 0 to pi over 3, pi over 3 to 4 pi over 3, 4 pi over 3 to 2 pi. Now, unlike the earlier trig problem where I was kind of using whole number radians, like 2, 4, and 6, I kind of went back to a more traditional method and picked values that were off the unit circle. So pi over 6 here, between pi over 3 and 4 pi over 3, I went with pi. And then between 4 pi over 3 and 2 pi, I picked 3 pi over 2. And when you put them in a calculator, of course, they'll just change over to decimal. But you get positive, negative, positive. So there we go, positive, negative, positive. That means we have increase, decrease, increase. So they're both critical numbers, so they both means they're certainly fair game to be maxes and mins. So increase to decrease means we have a relative max at pi of 3, f of pi over 3. Decrease to increase, we have a relative min, 4 pi over 3, f of 4 pi over 3. And so I'm sure I didn't label it here, but the scale of the graph is definitely pi over 3. So it goes up, increase to pi over 3, down to 4 pi over 3, and then back up to 2 pi. So the x goes from 0 to 2 pi, scaled by pi over 3s. Well, all right, that concludes this video on increasing and decreasing functions.